MOSFETs are commonly used in circuits where low power consumption is important to extend battery life. State and explain the property of MOSFET devices that makes them useful in these circuits. Now, it's a 2-mark question. The first mark is going to be for making the statement, and the second mark is going to be for the explanation. Now, this is a 2-mark question, so 2 points to be made here. The first one is that you have a high input resistance, and that's going to be your first mark. The second thing to say is that when it's in the on or off state, you're going to have no energy consumption or very little energy consumption. And that's your second mark. Figure 1 shows an N-channel enhancement mode MOSFET being used as part of a circuit for the water level alarm in a garden pond. When the gap between the copper strips is filled with water, the MOSFET turns on and the alarm sounds. And we've got the diagram here with our MOSFET in the middle. You'll see that there are those 2 copper strips that it mentions in the question. And when that space fills up with water, then that's when the alarm goes off. Explain the reason for the 1 megaohm resistor in this application. Now, the first thing to say is that this resistor stops there being a static charge buildup on the gate. And that's going to be your first mark. The second thing to say is that the gate voltage is going to be 0 volts when there's nothing between the probes. And that's your second mark. So nice, easy explanation there. The circuit is tested by immersing the copper strips in the water and bringing them closer together until the alarm sounds. VTH for the MOSFET in figure 1 is 2.4 volts. Determine the resistance of the water between the copper strips when the alarm sounds. Now, looking back at this diagram, you can see it kind of operates a bit like a potential divider, where you've got your 1 megaohm resistance on one part, and then the resistance of the space between the copper strips as the other resistance. And it's the ratio of those 2 resistances that gives a ratio of potential differences and determines how that 12 volts is shared. So let's write down the potential divider equation. Now, it's important that we determine here what is meant by V out, V in, R1 and R2. So let's just label that. So we've got our voltages there, V out being 2.4 volts and V in being 12 volts, the total supply. Now here we're saying that R1 is the 1 megaohm resistance that we saw earlier in the question, and R2 is the thing that we're trying to find. So we want to input all of our values and then find a value for R2. So let's rearrange this equation. So we end up with R2 is equal to V in divided by V out as a fraction, multiplied by R1 minus R1. Now what makes this quite easy is that R1 is just 1 megaohm, so we're ending up with a value in megaohms, so we can just use that 1 to our advantage. So we end up with an answer of 4, so 4 megaohms. Now, in terms of marks for this question, you'll get 1 mark for at least attempting to use the potential divider equation. So any reasonable attempt on this first line here will get you the first mark. And then your second mark is going to be for getting the correct answer of 4 megaohms. So 2 marks there. Describe what is meant by amplitude modulation, or AM. Now, there are 2 ways you can answer this question. It does accept a labeled diagram, but to make things simple, we're just going to say that the amplitude of the carrier varies in phase with the information signal or the audio signal. And that's a nice, easy 1 mark to start with. A radio wave has an unmodulated frequency of 120 kilohertz. It is amplitude modulated by a signal from an audio transducer of frequency 2.2 kilohertz. Calculate the bandwidth of the modulated wave. Now, we don't actually need the 120 kilohertz here. All we need is the frequency of the information signal, which is 2.2 kilohertz. And to find the bandwidth, we just multiply that by 2. Another easy mark there. Explain why frequency modulation, or FM, is not used for commercial radio transmissions in the medium and long wave bands. Now, the answer to this is that with frequency modulation, you need quite a large bandwidth, so you wouldn't be able to have as many channels if you were to use low frequency carriers, and that's basically what you're going to write down. Now, you kind of need all of that to get that mark. State and explain one advantage of transmitting digital signals using frequency modulation, or FM, rather than amplitude modulation, AM. Now, the first thing you can say here is that if you've got any noise, then the signals are going to get their amplitude distorted. And you can't reduce that very well using AM as opposed to FM. So that's going to be your first mark. And your second mark can be for saying that with FM, the original signal, you can actually recover it as long as the frequencies and the bandwidth are detectable, since there's no information in the amplitude. And that's going to be your second mark. So 2 marks there. Figure 2 shows a circuit that includes an ideal operational amplifier. A student uses this circuit to amplify the signal from the sensor before further processing by the system. Then we've got this diagram here of the circuit, which forms that ideal operational amplifier. Point X in figure 2 is said to be a virtual earth. Explain the meaning of the term virtual earth in this type of circuit. Now, the first thing to say about this virtual earth that makes it a virtual earth is that it's not actually connected to 0 volts directly. And that's your first mark. The second thing to say is that the voltage between the positive and negative inputs, which are these 2 points here, needs to be 0 or very small. Otherwise, you'll get a saturation. And that's going to be your second mark. The temperature sensor produces a signal that changes by 10 millivolts for every degree Celsius change in temperature. The signal is 0 millivolts when the temperature of the sensor is 0 degrees Celsius. The value of Ri is 22 kiloohms and the value of Rf is 270 kiloohms. Calculate the output voltage V out of the circuit in figure 2 when the sensor is at a temperature of 50 degrees Celsius. Now, the first thing that we want to do is work out that overall voltage change that's caused by the 50 degrees Celsius. That seems like the most obvious place to start. So you can see there, because it's 10 millivolts or 0.01 volts for every degree Celsius increase, but there's 50 of them, we're going to do 50 times 0.01. So it's a 0.5 volts increase there for V in. Now, in order to find V out, we need to use this equation. And then we just need to make the correct substitutions. Technically, you don't need to include the 1,000 parts on the 2 resistances because they're both kiloohms, they're both times 1,000. You could just do 270 over 22, but let's put it as explicitly clear as we can. And then you just need to rearrange to find V out. And there's your answer. So for this 2 mark question, your first mark will be either identifying that V out can be found using this equation. Another way you could obtain that mark is by working out the bit that we did at the start with the V in and the 50 degrees Celsius. That could also get you that first mark. The second mark is then going to be for actually working out the correct answer at the end. So 2 marks there. The circuit is powered by a minus 15 volt 0 plus 15 volt supply. Explain why this circuit will not detect temperatures above 122 degrees Celsius. Now, again, the only thing that we can do with that temperature is convert it to a voltage. So remember, we said that it was going to go up by 0.01 volts for every degree Celsius increase. So 122 degrees Celsius should, in theory, give us 1.22 volts. So at that temperature, we end up with 15 volts. So any temperatures higher than that, we're not going to get a further increase in the voltage output because that's all we were given in the first place. So 2 marks there, 1 for each of those points. A student suggests a modification to the circuit in figure 2 to form a difference amplifier circuit for a thermostat. The modified circuit is shown in figure 3. So you can see figure 3 here as a kind of modification of figure 2, but we've got an extra resistor there, a variable resistor, and also a battery just next to it. You'll also notice there's an extra resistor there. The output controls a circuit that switches the heater off when the output is positive. Explain how this circuit operates so that the heater switches off when the temperature reaches a predetermined level. Now, the bit that's user controlled is going to be this variable resistor. So what we can actually do is choose that particular level by controlling the potential difference using that variable resistor. So let's make that our first point. That's going to be our first mark. Now the equation that determines the output of the circuit is going to be this one. And that's going to be our second mark. And what then happens is when those two inputs have equal voltages, this V2 minus V1 becomes 0. So that's the kind of switching over point where the whole thing goes from positive to negative or negative to positive, depending on the direction that you're going in. So at that limit, i.e. when V1 equals V2, the output changes from positive to negative, and that will cause the heater to switch off. And that's going to be your third mark. An engineer uses a copper cable to connect an intercom system between her office and workshop. The signals have to travel a long distance, and she finds that the interference, the hum, from the main supply is a problem. She reduces the interference using a filter tuned to the frequency of the main supply. The mains frequency is 50 Hz. Figure 4 shows her solution, which is based on a parallel LC resonance circuit. And we've got the diagram there. You can see there's an inductor, which is labeled L, a capacitor, which is labeled C, and a resistor, which is labeled R. The engineer uses a 2.0 Henry conductor. Calculate the required value for C for the filter to operate at 50 Hz. Now, all we need to do for this question is use the correct equation, which I'll write down first of all. So the frequency is equal to 1 divided by 2 pi times the square root of the product of the inductance and the capacitance. So we just need to substitute the correct values and then make the correct arrangement to get the value of C. What I'm going to do is I'm going to rearrange the equation first and then put the values in. So C is equal to 1 over 4 pi squared F0 squared L. So making the correct substitutions, and that should give us a value of 5.07 microfarads. Now we should round that to 5.1 because the values given to us in the question are to two significant figures, so our answer should be to the same number of significant figures. Notice I've put times 10 to the minus 6 because the answer needs to be in farads. So for this question, you get 1 mark for the correct rearrangement of the equation, and a second mark for the correct answer at the end. So 2 marks there. Figure 5 is the response curve for the inductor-capacitor circuit, which shows how the PdV across the inductor-capacitor circuit varies with frequency. Now, we've got figure 5 here, with a very clear curve there, with a peak at 50 Hz and a bandwidth of 2.5 Hz. Calculate from the graph the Q factor of the inductor-capacitor circuit. Now, to calculate the Q factor, we use the following equation. Q factor is equal to F0 divided by FB. If we go back to the diagram, then we can find out what those values are. So you can see here that F0 is 50 Hz and FB, or the bandwidth, is going to be 2.5 Hz. So making those substitutions, we end up with a value of 20. Bear in mind that this doesn't have a units because it's a value in Hertz divided by another value in Hertz, so the units cancel. So to get the mark on this question, you do need to get the right answer at the end. So 1 mark there. The inductor is replaced to one that has an inductance of 8.0 henries and a lower resistance than that of the original inductor. The capacitor is not changed. Describe how this change affects the response curve of the inductor-capacitor circuit. Now, there are 2 points we need to make here. The first one is about the resonant frequency and what that changes to. That resonant frequency is going to become 25 Hz. That's going to be your first mark. You'll notice that you can obtain that 25 Hz by putting 8 henries into that original equation rather than 2 henries. You'll notice that that change in inductance is by a factor of 4, but the inductance in the equation is within a square root function. So a change by a factor of 4 will actually give a frequency change by a factor of 2 because it's a square root of 4. The second point to make is that the peak is going to be higher than the original at that resonant frequency. And that's going to be your second mark. So 2 marks there, 1 for each point. Compare the advantages and disadvantages of optic fiber and copper wire for transmitting information. Now, the way I'm going to approach this question is I'm going to break it down into 3 parts. The first one being the physical properties of the material. The second one being in relation to external interference, and the third one being in terms of the material's ability to carry a signal. So let's examine the first one to begin with, physical properties. Now, there are 2 points that can be made here. The first one is in relation to corrosion. So we can say that with a copper wire, it will corrode. It's subject to weathering unless you protect it well, whereas something like glass, completely different chemical makeup, is not going to corrode, so it's more easily preserved. The second point to make under physical properties is in terms of the weight and the cost. Now, copper is quite heavy and quite expensive, whereas glass is cheaper, and you can also make thinner cables out of it than with copper. The only problem with glass is that it's quite difficult to join together. So that's all we need to say in terms of physical properties. Let's move on to external interference, which is a little bit more complicated, but we can still explain it quite easily. Now, the first thing to say in this category is that in terms of security, a copper cable is quite easy to take the signal from. Because it's just an electrical signal moving through a cable, you can just attach a wire to it and you can get some current to move down that extra connection without interrupting the original signal. Whereas with a fiber optic cable, it can only work if the cable, realistically, it can only work if the cable is fully intact without any breakages. And the only way to obtain that signal from the outside is by breaking the cable. Bear in mind that it relies on total internal reflection. The second point to make is in terms of electromagnetic interference. There's a lot of noise that you can get in a copper cable, whereas there isn't really anything that can interfere as such with a light or an infrared signal in a glass fiber optic cable, because remember, it's quite a specific mechanism that it works on. If it's possible for light to enter that fiber optic cable and cause noise, then that must mean that it's also possible for light to leave the cable. But we don't build it in that way. We build it in such a way that light can only be totally internally reflected and not refracted into or out of the cable. So those are your 2 points for external interference. We're now going to move on to signal carrying properties of those two types of cable. The first thing to compare between the two types of cable is attenuation. Copper cables are subject to quite high attenuation in comparison to glass fiber optic cables. However, the pulses in a glass cable can suffer what we call smearing. So that's the first point to make on signal carrying properties about attenuation and smearing. The second point to make is on bandwidth and information carrying capacity. So you can't actually get very many channels on a copper cable, but you can get a lot more on a fiber optic cable. So you could say a larger number of channels or just a larger information carrying capacity. And that's the second point to make. Now you'll notice that this is a 6-mark question. It's not as simple as 1 mark per point, unfortunately, because there are marks available for spelling and grammar, quality of written communication. So I'm just going to write that at the bottom. The way I would look at this is obviously if you've got all 3 of those segments covered in sufficient detail, then you're going to get 6 marks, I would say. And then moving down from there, if you have lots of detail in 2 of the sections, but one of them is lacking slightly, then you might drop a mark there and go down to 5. And then I think each section down from there where you're lacking detail is going to remove you a mark. But if there's a section where there's no detail at all, or nothing that's worthy of any marks, then that might lose you 2 marks. The Boolean equation for a particular logic circuit with inputs A and B and output Q is Q is equal to brackets A dot B plus brackets A bar dot B bar. Table 1 shows intermediate logic signals for the circuit and the overall output Q for all combinations of the inputs A and B. Complete the missing 2 entries in the truth table. Now, if we have a look at that equation back at the top again, we can see there that the value of Q is the sum of A dot B and this A bar dot B bar. So all we need to do is look at the second to last and third to last column, which are these two columns here, because those are the ones that we need to sum to get the value of Q in the last column. So the examples are in the second and fourth rows. 0 plus 0 is equal to 0, and 1 plus 0 is equal to 1. So if we look at the first row, we can see that it's going to be 0 plus 1, so we're going to end up with a value of 1. And then for the third row, 0 plus something must equal 0, so the something must be 0 for that to add up. Now you need both of those to be correct to get your mark. Complete the diagram in figure 6 to show the logic circuit that has the same function as the Boolean equation given in part 6. Your circuit should contain only 2 AND gates, 2 NOT gates, and 1 OR gate. And this is a 3-mark question. We need to connect those terminals up. Now let's first of all look at what these gates mean. The first one, an AND gate, is where if both the two input signals are on, then the output signal will also be on. So if you get a 1 on each of the input terminals, you get a 1 on the output terminal. Now for a NOT gate, each NOT gate has one input, and it basically does the reverse on the output of the input. So if the input is off, the output will be on. If the input is on, the output will be off. And then the last one is an OR gate, and this one will only have an output signal on if either one input or the other input is on, but not both and not neither. So we need to think about how we're going to structure this using that combination of gates. Now this circuit needs to give an output Q if both A and B are on, or if neither A nor B are on. So let's start off by drawing an OR gate next to the outputs. And that will give you your first mark. Now for the system to work, the two inputs onto this OR gate need to be in such a way that either one can be on or the other can be on, and that it will give an output Q. Now that condition is going to be A and B are on, or A and B are off. So let's put the AND gates as the inputs to the OR gates. Now one possible connection, let's make this the top AND gate, is if both A and B are on. So if we get a signal in A and B, that AND gate will switch on. What we also need to do is make sure that the other AND gate meets the correct criteria, and that is when they're both off. So this is where the NOT gates come in. The reason we need these is to activate the AND gates when they're both off. So if they're both off, A and B, then the NOT gates will invert that signal and give on inputs to that lower AND gate. So let's connect those up correctly to the A and B inputs. Remember that those types of gates only need one input because they're just inverting whatever they get, so providing the opposite for the outputs. So your second and third mark are going to be firstly for connecting A and B to the AND gate, and your third mark, and secondly for connecting the NOT A and the NOT B to the AND gate as well, so the NOT signals. So just to summarize, following this circuit along, we can see that if A and B are both on, then the top AND gate will be supplied with the signal. The bottom AND gate will not be supplied with the signal because, yes, there will be a signal that reaches the NOT gates, but then they will do the opposite. So the bottom AND gate will receive 2 off signals. But then that's a good thing because the OR gate at the end will receive an on signal from the top AND gate and an off signal from the bottom AND gate. So because it's an OR, it needs to be one or the other. We will get a signal from Q, just like we saw in the truth table at the top. Now let's contrast that with if both A and B are off. What we will find is that obviously there will be no signal supplied to the top AND gates, which is fine. But for the bottom AND gate, the 2 NOT gates will receive off signals which means that they will convert them into on signals. Remember, they do the opposite, and that will then put 2 on signals into the bottom AND gate. And what that will mean is that, in opposite fashion to what we just discussed, the OR gate at the end will receive an on signal from the bottom and an off signal from the top. And because it's one or the other, it will get the signal Q. It's even easier to work out what would happen if A or B was on and what the signal would be, because there wouldn't be sufficient criteria for either of these AND gates to give an on signal. So there would never be an on signal from one AND gate or the other. So there would never be a signal from either AND gate when either A or B is on. So Q will always give an off signal. So 3 marks there.